Okay, this is a pretty rare beast. It is a tritium gas monitor. It's pretty old. It's going back to the 70s. I've never worked on this or these instruments. I did work for the company that made these. I worked on its successors, which were actually quite a bit more sensitive than this one. Long story how I ended up with this. Not get into that. This is a Triton model 1125, serial number 1000. I don't know if that means that this was the first one or not. It may be that they got this back for some reason and decided it was a landmark or a milestone and decided to keep it. Well, they did. Nevertheless, somehow I ended up with it. This thing, like I said, made in the 70s. All mil spec. It's probably why it looks a bit odd. Boots around the toggle switches, probably mil spec knobs even. From what I'm told, every single component had to be certified by the mill. I mean, even this power jack, this is where the power cord goes. Hot, neutral, and ground. Although this is actually meant to be a portable instrument. You see this cleat and this one down here? To those you would attach a strap to carry this beast around. Now this, I mean, it's not small, you can say. It's not very light either. It's got a pretty good bit of weight to it. It's got a battery in it. You see relative size, right? Not a small thing to be huffing about. But nevertheless, that's what they wanted. These were this is a commercial version. The model being 1125, that was a commercial version. Nevertheless, it is built to the same specs as the military required. They had a different part number for it, or a different model number, but nevertheless, it's, I'm told by very reliable source that this is built the same way, and looking at it you can see it. Now the way it's sitting here right now would not be the way it would be operated. It would be operated in this position. Kind of awkward to show front panel controls and stuff that way, so, but it's meant to be carried. It has a battery in it. More on that later. It's a tiny little meter. The sensitivity of this instrument is not really high compared to what I've worked on. Like as I said, I've worked on subsequent models of the same, and boy, maybe an order of magnitude more sensitive than this instrument. This full scale in the most sensitive range times 1. The full scale is 100 microcuries per cubic meter of air, and basically, it just sucks air in, filtered, I would assume, pulls it through some chambers, more on that later, and just exhausts it. The Navy wanted these because of nuclear reactors on submarines and ships. For whatever reason, they wanted to know, or they wanted to detect the presence of tritium, which is a byproduct of certain nuclear reactions. Whether it was intended or not, I don't know. I know they do use tritium, but for whatever reason, the Navy wanted to know if they wanted to be able to have an instrument to detect the presence of tritium. And tritium, it's 3H, hydrogen 3 if you like. It's a hydrogen atom with 2 neutrons and 1 proton. And it is a radioactive gas. Mildly. It decays into 3H, or helium-3. But when it does so, it emits beta particles. Now, it's a pretty weak beta emitter. Those particles can only go maybe 1/4 of an inch or so through air. They're not going to get through your skin. Pretty much harmless with that kind of exposure, but it's probably not something you want to inhale. I mean, even if you did that, you'd take quite a bit of it, I reckon, to cause any problems. There are issues with tritium, but for whatever reason, they wanted to know or sniff out, if you like, where there might be tritium. Either in a sub, or maybe they just wanted to detect that they were actually producing this stuff. This does that. The controls, yeah, not much there. As I said, it has a battery, and it has a battery test. There's a scale on the meter for the battery test, circuit test. There's another little scale for that. I'm not sure exactly what that means, but this thing does develop a number of voltages that need to be present for this thing to work, and I reckon, I'm guessing actually, that in circuit test mode, that it combines all those voltages that should, on this meter, put the needle right about there. If it's off, that probably means that one of the voltages that is required is not right. 3 ranges, times 100, times 10, times 1. As I said, times 1 is 100 microcuries per cubic meter of tritium. It also has this alarm function where some way, and I'm not exactly sure, I have powered this up briefly, but I'm not sure exactly how the alarm function works. I know what it's for, but I don't know exactly the method you use. There's a horn in the back that presumably would go off if the alarm goes off. Now, the alarm would be to set up some point in some scale where if it gets above that reading, it lets you know. It's like, okay, there's a big problem here. Okay, that's adjustable. I reckon that when you put it to reset, you turn the set knob, you set where you want the threshold to be, and then go back to normal mode, one of the 3 ranges, and if it gets above that point, then you're going to hear it. It's going to let you know, in case you're not paying attention. A couple of nifty fuses, fuse holders. Fuses are in there, and if either one of these blows out, it opens a circuit that allows lamps to light up in these guys to let you know that something's wrong. You blew a fuse. There's a flow meter here. A little tough to see. Just a ball bearing in a acrylic, what appears to be acrylic piece, to let you know there's a pump in here that draws air in and pushes it out. Draws it in, passes it through a number of chambers, and then pushes it out. If that pump fails, you have an indication of that with this flow meter. Pretty binary device there. It's just a steel ball in a tube inside of here. This will only work when this is sitting in the position that you would have it in when you're carrying it. This is the inlet, that's the outlet. So that to me is a flaw, because if a piece of tubing comes or disconnected inside, it could still draw air, but might still be showing flow on the meter here, the flow meter. So I'm puzzled about that, but there's more to it. These things are so sensitive. This one, not the most sensitive I've worked on, but I will tell you, it is the closest doggone thing to magic I've ever been around. The exquisite care that must be taken to make these beasts work. So let's have a look inside. Okay, basics. Power supply. Now, from the line cord, looks like all the power from this thing can be supplied from this tiny little transformer. Doesn't take a lot of watts to make this work. There was a battery, as I said earlier, associated with this thing, and that was mounted down here in the bottom. It was a 12 volt NiCad pack. Very problematic from what I've been told, and certainly understand. I've removed it. When I got this, it was in there, but corrosion was an issue, so out it goes. Don't need that in there. So, and down here, power supply, all mill. Everything, every component on here has been qualified, or at least had been. Nifty little potted toroidal transformer, puts out a number of voltages that this beast needs. All transistor. There's not a single integrated circuit in this thing, because they back then, it took too much to get them approved. Mil spec caps, really sweet. This here is a voltage regulator. It's a neon-based voltage regulator. I read that there are small amounts of radioactive product in these to make them function properly. Something to do with this coating that looks black. That's an 82, if I recall, 82 volt regulator. More on that later. Some voltages in this beast need to be fairly precisely regulated, and whoever designed this did an excellent job. The whole thing's conformally coded, mil spec. As I said, every component in here is mil spec. Every damn one, from what I'm told. Oh gosh, other interesting stuff. Look at these fuse holders. That's just crazy, but those are nice. Good the way they did that. Other features, okay. This, had to check to make sure you can see it. This is an electrostatic precipitator. This is where the air comes in. It goes through this, and there's a sort of a tortuous path. This thing's made up of a number of concentric tubes, metallic tubes that are alternately charged. I believe it's something like 300 volts to ground, and that serves to remove electrostatically charged particles as well as ions from any gases coming in, because you don't want that going into the ion chamber. You can see this tubing's kind of actually quite a bit dodgy. I think it's neoprene. I'm not sure. I'm leaving it as it is because I believe this is a museum piece and I don't want to change anything to make it work. I know the electronics work, but there are things that do not. And one of the problems it has is with this tubing, but I'm going to leave that alone. So gases come in through the precipitator and enter the tritium chamber, which is an ion chamber. Inside this box there's a rod, probably of stainless steel. I've never actually looked in this particular box, but other electrometers I've worked on, ion chambers I've worked on for this company, the rods were, it's just a simple rod. They about maybe a little over 1/8 of an inch diameter rod that extends from the base up to just about the top. So the tritium, or the gases, air, enters into this chamber. If there's any tritium present, or radon or any other radioactive isotope gas, will ionize other air in the chamber. And this box is charged with the electrostatic charge, meaning the voltage. In the case of this, the tritium chamber, it's about, well, it's 82 volts. And that's what that regulator thing was for. The purpose being that the charge on this box causes ions produced by the radiation produced by the tritium are driven to or from that central rod. That central rod is connected to, back here, an exquisitely sensitive amplifier that drives, its output drives the meter, as well as the alarm circuitry. There's another box, gamma chamber. Now, in an environment, say on a nuclear sub, where you might want to be sniffing for tritium, you will likely also have gamma radiation present. Well, you don't want to measure that with this device. You want to measure tritium and just exclude any other ionizing radiation. So you want this thing to not respond to gamma radiation. The way they do this is they have two chambers. One chamber has the gas, the air that you're sniffing going through it. The other one does not. This other chamber is charged oppositely in polarity to this one electrically, and also has a different charge on it, because gamma radiation is so much more penetrating than what they're looking for. So in addition to that, there's another rod in there. This one has two rods in it. One is just like this one. It's meant to pick up the ions. The other rod is a compensation rod that gives you some way to, if you adjust the potential on that rod inside this can, gives you a way to balance these two chambers so that gamma radiation coming in affects this chamber and this chamber equally, at least as far as the sensing mechanism goes. And that way any gamma radiation coming in is canceled out and therefore does not show up on the meter, where any tritium gas entering this chamber but not entering this chamber will register on this meter. So it's called gamma compensation. Pretty nifty stuff. There's a pump. This is a little DC motor, drives a little pump. It's seized up. It no longer works. Number of reasons that might be, but I just decided to leave it alone. His whole job is to just move air through the tritium detecting ion chamber. In the back, in here, and I've never opened this up and I'm not going to, is the electrometer. There's down here a sound alert, a horn, This is the beeper that goes off when the alarm setting gets, the measurement gets past the threshold which you've dialed in. Inside of here, in this one, now this is almost all solid state, meaning it uses transistors. There are, as I said, there are no integrated circuits in here, but there is a vacuum tube, and that's really the meat and potatoes of this beast. Here's a circuit board from a similar instrument, not this one, but one I've worked on. Now, this one does have an integrated circuit on it, but it also has this vacuum tube. This is a 5886, a CK5886. You can look that up. This generally made by Raytheon. I think some others did produce it, particularly later. I have worked with the instrument that has this board in it. You can see the control grid of this is attached to Teflon insulators, which, oh my God, you had to be so careful about cleaning. The feedback resistors with these, basically this is an op amp, just a very, very, very exquisitely high impedance input one, and the method you had to go through to get these things to work are interesting to say the least, mostly extreme. I don't remember why I have this one. I think it was just something I got from scrap material. Later models, this went out of production some while ago, not that long ago. But there are other methods these days, more modern, and another is something like this. That is a dual MOSFET, 3N165 to be specific, and on this board there is indeed an op amp. What is that beast? LM 725. And also shown here is one of these high meg resistors. Now, when I say high meg, that resistor is, and I kid not, that resistor is 3 million megohms. Now, I know that doesn't mean much to the lay person, but let me tell you, man, that's ridiculous. That's like ludicrous ohms compared to what we are used to looking at as resistors. 10,000, 100,000, 350,000, a meg ohm or two. This one here is 22 million ohms. This thing is 3 million ohms. And that determines the input impedance and the gain of this amplifier. And that's what it takes to make these electrometers work, these ion chambers. Pretty sensitive stuff. So, nothing much else. There's a rectifier here, charges the battery, which is, as I said, removed. Underneath, again, this calibrate that pretty much just adjusts what the meter setting is for a known amount of radioactive gas, in this case tritium, that is injected into the chamber. And compensate has to do with that gamma compensation thing I was talking about, where you want to eliminate the effects of gamma radiation on this instrument, which will penetrate the whole thing, as much as you can. This is not the best design, having only 2 chambers. Subsequent instruments I have worked on had 4 chambers, and you can imagine the geometry, the 4 chambers set diametrically opposed, I guess is the best way to put it. No matter which direction the instrument was facing from the gamma source, it would better compensate for the presence of that gamma radiation. This one might not, because if the tritium chamber, that is this chamber, if you're facing the reactor and the reactor is this way and there's gamma coming from it, gamma's going to get into this but not into this, or well, not as much. Same thing, turn it around, now the gamma chamber gets more gamma radiation than the tritium chamber, so you get a negative reading. You don't want that. So you had to be careful, I reckon, that which position you were facing. I don't know as far as magnitude how much it mattered, but it's a good start. But subsequent models had 4 chambers, 2 gammas here, 2 tritiums there, and it did a pretty good job, and I played with it and it really did work. Standing in a room with a cobalt 60 source, adjusting the gamma compensation on an instrument much more sensitive than this, and it really did work. You could spin the instrument around, although we had prescribed distances and positions to calibrate them in. It did a pretty doggone job of eliminating the gamma signature or readings, and just allowing the tritium gas to go in and measure that. Now, I had to calibrate instruments such as this, and to do so we actually had to use tritium gas. Tritium, from everything I've read, my own personal experience, it's not totally innocuous, but it's fairly safe to work with. It's a low-level beta emitter. It can't go. The betas emitted from tritium can't get more than 1/4 of an inch or so. So it's not going to get through your skin. Even if you inhale it, the risk is fairly low. Not something you want to inhale, but if you did, you're probably okay. You're inhaling stuff like that anyway. Tritium half-life is about 12.5 years. So it's difficult to store. It's a useful thing for certain stuff, but it does not last long. I actually have some, maybe. What we used to calibrate these things is tritium, and there were these calibrators. Now basically the calibrator was a closed loop. Gas goes in and gas goes out through a closed loop of the instrument you're calibrating or testing. And you'd introduce an aliquot of tritium. You adjust this pressure gauge and regulator to a specific pressure. This is a lecture bottle that contained tritium. You would adjust to a certain pressure, introduce that into a specific volume of tubing in this calibrator instrument. Very simple things, 1,000 piping, and introduce that into the loop, and you would expect to see a certain reading on the meter, and that's how we calibrate the things. And if it was high, you'd turn the pot and pump it down. If it was low, opposite, you turn it, pump it up, and it worked pretty good. Now, when I got this cylinder, it's a long story again how I got this, and the gauges and the regulator, but it did contain tritium under no pressure, meaning atmospheric pressure, but there was tritium in here. It's quite a long while ago. The half-life of tritium being 12.5 years. Yeah, well, this is less than a half of the tritium that it used to be. Tritium decays into helium-3. H3 decays into He3. And when it does that, it increases the pressure. It's bigger. Somehow. Don't ask me. And I have cracked this valve with the gauges off, and indeed there was a relief of pressure. I don't know if it was just because of temperature or because of the decay from helium-3 hydrogen-3 to helium-3. I don't know. But it's probably a pretty good guess. The temperature's rather constant down here in the dungeon. Interesting. So, other things, I mean, the way they laced these cables, that took so much work and patience. There's some wafer switches in here, all ceramic. Even the pots, the control pots, ceramic. Probably Alan Bradley, not sure. Can't see right now. Interesting. The gamma chamber would have had there's a port here, open to the air, but most likely, and if I'm not mistaken, did have in this instrument a desiccant pack to make sure that the air in that chamber was dry. Humidity, moisture screws up electrometers like nobody's business. Let's see, what else? One of the niftiest logos I've ever seen. Hard to see. Maybe let's see if I can zoom in on that, because it's pretty cool. And try to get a focus. A Triton. But yeah, one of the coolest types of instruments I've ever worked on. And do miss it. Parts of it, most of it. Like I said, they were tricky. And if you could make one work, you were in Lake Flynn. See you.